Good afternoon and welcome virtually to Old Dominion University and its remote experience for young engineers and scientists program known as REYES. My name is Giovanna Gennard, Assistant Vice President for Public Relations and co-chair of REYES, and I will serve as your host for today's event on Rocks in Space, Zap Them All, featuring Luisa Fernanda Zambrano Marin. The purpose of the Global REYES program is to offer free virtual learning experiences that increase literacy in science, inspire and train future generations of STEM-age students. Today's discussion with Luisa Zambrano offers us insight into Puerto Rico's Arecibo Observatory and their work blasting near-Earth rocks with radio waves at the frequency of your microwave, but much more powerful. Throughout this webcast, you may submit questions through the Q&A box on your Zoom screen. And following the lecture, we will answer as many of your questions as time allows. And now, without further ado, I leave you with Luisa Fernanda Zambrano Marin from the Arecibo Observatory Planetary Radar Research Group. Welcome, Luisa.
Hello, how is everybody doing today? Oh, my goodness. I hope everybody can see my screen and hear me good. I can't see the participants, so I'm just gonna go ahead and start. Like Jimena said, my name is Luisa Fernanda Zambrano. I'm part of the Planetary Radar Research Group at the Arecibo Observatory here in Puerto Rico. And I'm gonna talk to you a bit today about rocks in space, like you said, Zap Them All. But before I start, I wanted to ask all the participants, if you can, to please put your headset on or have your sound so you're able to listen to see this video with the appropriate sound, because it really conveys a message that I want to start with all of you. It's only about 2 minutes long. So.
We are the explorers. We have a need to find what is out there. It is a drive inside each and every one of us. The drive to wonder, to push the boundaries, and to explore. We expanded across our lands, settling new frontiers. We took to the oceans and learned that we could cross treacherous expanses in the pursuit of discovery. And then we took to the skies and flew. But that wasn't enough. We left the planet and redefined what was possible. We flew in space. We walked in space. What once was a melodramatic flight of fantasy became reality. Then, a new generation of spaceships captured hearts and minds for 3 decades and helped build a castle in the sky that is our lasting home in space. We have always looked up. For centuries, we wondered what was on the other side of the sky, and we have begun to answer that question. We have learned that all the exploration humankind has achieved is only a beginning. Right now, men and women are working on the next steps to go farther than we have ever gone before. New vessels will carry us, and new destinations await us. Everything we have ever accomplished leads to this moment in time, where exploration will now take us to the planets and the stars. Our nearest neighbors in the night sky have beckoned us, invited us, dared us to reach for them. We are the explorers. Throughout our history, we have taken both small steps and giant leaps in that pursuit. Our next destination awaits. We don't know what new discoveries lie ahead, but this is the very reason we must go.
Okay, so I hope you enjoyed that video. And the reason why I showed this video is because all of you and all of us, pretty much, we were born after Apollo. Apollo was the first moon exploration program from NASA. And it really gives a different perspective to everything we do in society now, that versus how society was before. So I just wanted to start with that, although the topic of our conversation today, conversation today is rocks in space, asteroids, near Earth asteroids, and what we did with radar. I wanted to show this so you can see that it's just much greater, and we have so many parts in space exploration that are not just astronomy or planetary sciences. So today, like I said, we're going to talk a little focused on asteroids and give you some general information about our solar system, how we saw these objects from Arecibo, and what the radar technology can tell us about asteroids. So I think if you can feel free to interrupt if there's specific questions that we should address while we're there. So just let me know that you can unmute yourself. So let's start with where are we, right? So I think most of you know, most of us know by now, right? Our generation knows that if this is the galaxy, our galaxy is a spiral galaxy that called named the Milky Way, our solar system is about where the arrow is pointing. And this galaxy is only one of hundreds of thousands of millions of galaxies. As we can see in this image here of the Hubble Space Telescope, this is a deep field image that basically is a mosaic of a lot of data. So it really gives you a perspective of how deep and how majestic the universe is. So having now the James Webb Telescope in orbit would help us learn much more of these objects in space, galaxies, supernova, planets, other solar systems, and also about asteroids. So that's one of the cool things that James will be able to learn more about objects that are really far, like trans-Neptunian objects or Trojans. So we believe the solar system was formed by the interaction of a supernova explosion with the planetary nebula that we had. Then it formed something called the protoplanetary disk. That is kind of what this image depicts. But some of others see it as, this creation that took place. So what do we know so far about this? What do our regeneration know? So this is an orbit, say a planar orbit diagram of our solar system. You can see Jupiter, and in between Jupiter and Mars, there are all of these dots. They're called the main asteroid belt. And these little objects that you see yellow here and yellow back here, they're stuck in this orbit, either trailing or following Jupiter. And there's a couple of them. Earth also has a few of these Trojan, say, objects that follow or trail the Earth, or lead the Earth, go in front or behind. So we really care about the objects here in purple, the near Earth objects, right? Because they're the ones that could interfere with Earth. Although we now know that there have been interstellar objects that have visited our solar system, like Oumuamua a couple of years ago. So this is how we kind of imagine the orbit of the Earth from the side. We know that some planets have a tilted ecliptic plane. And this will be in a planar view where we don't see those tilts in the ecliptic plane. So it'll be a little bit harder to see the orbit paths, understand the orbital paths of the asteroids, but it's still pretty good, like I will show you. So these asteroids, these rocks in space, they are not all the same. They come in different shapes, they come from different sizes, some come alone, some come in pairs, some come in triples. So we actually discovered Arecibo before the Hurricane Maria, which was a really devastating hurricane here in 2017. We observed the asteroid Florence, which happened to have two satellites traveling with it. And our learning of asteroids has improved so much that we were able to send the first sample return mission from NASA, and it went to the asteroid Bennu. Bennu was actually observed with radar Arecibo in the 90s, and because of the rate of the shape model that was derived from the radar data, is that more studies were able to be done, and Bennu was selected as one of the potential objects for this mission, and finally obtaining that. fantastic opportunity. The mission is named OSIRIS-REx for any, is right here for any of you that would like to see more info on the sample return and what's going on there. If I'm going too fast, also let me know. So like I was mentioning before, when we look at the planar view of the solar system, we can't really see all the inclinations. So really good thing that we have computer generated graphics nowadays, because imagine in the 1960s and 50s, all of these diagrams and designs and calculations needed to be done by hand. So it really makes you appreciate how complicated some of this math was and how easier for us to resolve it with computers now, once we know the basics of math and the basics of physics that can be applied to this. So you see that the orbits of the asteroids are not the same way, right? They come in different angles, inclinations, sizes, and that tells us, of course, how often it'll come by Earth. And there's a special group of these asteroids that are called the potentially hazardous asteroids, not because they're going to impact us and destroy us, but because they're objects that are greater than 140 meters and that can get closer than 19.5 lunar distances. So it means that their orbit could intersect with Earth's orbit, but not at the same time that they're in the travel path. So those objects that could have an orbit intersection and could graze by Earth or impact are called virtual impactors until we have enough data to actually track and know where they're falling. We actually had about 2 weeks ago, we were able to measure a virtual impactor when it was just a few hours before landing on Earth. So that's a great advantage, something that up to a decade ago, we were not able to do. So this is a really cool diagram from the Canadian Space Agency. Almost every big country in the world has a space agency. So it's not only NASA. We have the Canadian Space Agency, the Mexican Space Agency, the Australian Space Agency, the European Space Agency, so I could keep going. But one of the important things is that all of these organizations have education material that you can also access and look at resources and things you would like to do in different languages as well. So let's focus on this one. It's about differences of these space rocks. Okay, so the comets are those rocks that have ices on them. Ice is not only water, there's other types of materials that can be ice. Then an asteroid is actually a rock while it's in space. Some comets release all of their gas, all of their ice, and became also asteroids. Once the asteroid is coming into Earth, it's got a potential of coming into Earth, we call it a meteor. And once it enters the atmosphere, is crossing, while it's crossing, it's called a meteor. And if it explodes during the atmosphere, we call it a fireball. And once it hits the land, it's called a meteorite. So what you pick up from the floor, from the fall location, it's a meteorite. So just really quick on comets. The comets, you not only have this, what you see here is like a tail, is because, like I said, they're made of these gases, of these ices. So what happens to ice when it's heated, right? So if we go to, when the process happens really fast, what do we call that process? I don't know if you can answer, but if you can think about it and remember it, it's called sublimation. So when this happens, all that gas, all that ice becomes gas right away. So you see this tail of particles on the white, right here on white, but it also has an ion tail. That means that there's electrically charged particles. The ion tail tells you the direction of the magnetic field, the solar direction of the magnetic field of the sun when it's hitting it. So a lot of cool things we can learn. We also theorize that life water could have come to Earth via cometary impact. When we talked before about rocks in space and the main belt of asteroids, which is between Jupiter here in orange and the Earth in Mars, and we go further out, Jupiter here and Mars here. Go further out, there's another belt of these rocks that's called the Kuiper belt. The solar radiation, it's much less there, right? As the wave if electromagnetic radiation or pretty much any wave expands, it loses energy in that travel. If we go all the way up further up to where the heliopause, before what we think the heliosphere ends, basically up to where the solar wind can reach, it's called the Oort cloud. So we think that comets get formed mostly in the Oort cloud, and then they travel inwards into our solar system. These pictures are really good pictures from the mission to Comet 67P. You just see the plumes right there of the areas where the sun is illuminating it. So it's really spectacular. There's really good animations. Just search Comet 67P and you'll see like great things. So why do we want to research all of this? Why do we want to know about these rocks and comets? Well, we think in our community that we are the first part of human civilization that could potentially prevent or foresee a possible impact of an asteroid that could damage Earth. We know that there's been at least 4 massive extinctions events on the Earth, and some of those were caused by meteorite bombardment or asteroid impact. So we want to try not be the dinosaurs, like we say in our research group, but be able to foresee or mitigate if this was to happen. Here's an image of the meteor crater that is very common. But these big rocks, they don't come to Earth all the time, right? What we do get, it's meteors entering the day to Earth every day. From objects that are 1 millimeter in size, there's every 30 seconds, there's little space dust particles that are interacting. Objects that are about 1 meter, they come into every year. And then we start wondering, well, where are all these objects? Well, remember that the Earth is mostly water. So they fall in water, we can't really find them. So we do have maps of the main landing sites. And now we have really good technology to measure them when they're entering Earth. So that's one of the things we did at Arecibo. We do now at Arecibo, we have a meteor radar, which with the Atmospheric and Space Sciences group, it's able to measure when these meteorites are coming into the atmosphere and see what minerals or what material is being deposited in the atmosphere as they come in, and what are those repercussions, if anything, on that higher atmospheric systems. So, as you know, the Arecibo Observatory main instrument was this radio antenna here that had what we call a Gregorian dome, hanging up about 150 meters from the reflector. So when the platform fell, all of the instruments used for planetary radar and astronomy were lost. But like I mentioned, we do have other groups of instruments that are mostly for space and atmospheric sciences. So this is how it used to look. You could go from the visitor center area, walking in this catwalk up on the platform, or there was a little cable cart that will help transport instruments or fix things. And under the almost 40,000 individual panels, there was its own biosystem that formed, like little ecosystem that formed from when it was built. So how radar works, like what did we do there, and how did we get these pictures of asteroids or information from them? So what we did is that from our Gregorian dome, we produced, like I mentioned on the talk title, we were able to produce an electromagnetic wave that was at a frequency like your microwave at 2.8 megahertz. So this was the wave. We beam it up, we zap it, it goes down into the dish, reflects back, hits the object, we get the echo, and then we're able to transform that echo, that electromagnetic signal, and extract something that will be like what we see as an image, but it's not necessarily exactly how it looks. So all of this really depends on how far the object is. We are able to tell you exactly with a very good precision how far the object is in reality from us than what was expected. So just to mention, Arecibo, the radar systems in general, they do not discover near-Earth asteroids. We're able to characterize them. They are discovered by infrared and optical surveys. And from there, once they get their detection, we're able to observe them. And I'll ask you at the end if you know why are asteroids only detected with optical or infrared. So that round trip time that we receive, that time it takes a signal for it to come back, tells us exactly how far it is, like I mentioned. It's all by the principle of the Doppler effect. So I know most of you have experienced this effect and probably did some math in it. When you hear an ambulance, as it approaches you, it sounds louder and louder, and as it goes away from you, it sounds less and less. So it's because the person as it's receding hears a lower frequency, and as it's approaching you, you hear it at a higher frequency. So we use that to also create what we call delayed Doppler imaging. That is basically if we're able to have really good signal to noise, meaning what we transmit, we get back a lot of it. We don't lose a lot of it, and it helps us know more about the surface. So things we want to know about these objects would be how fast they're rotating, how big they are, maybe what are they made of. You know, could we get an idea if it's rough, like a porous stone, or like one of the rocks in the beach, or is it solid like an iron ball? So with radar, we're able to do many of these things. We can see shapes, we can see spin, we can see rotation and size. So for example, this object, 2014 JO25, remember I told you they're not the same. They're not all spheres, or they're not all elongated. They have different shapes. These ones we call contact binary because they look like two different rocks that got stuck together, or maybe they were created like that, or maybe they came into contact and then stayed there. We can also tell information about the surface properties, like does it have concavities, or does it have little mountains? This one is for asteroid Phaeton. This is the second largest PHA that has been observed. It's going to be the target for the Japanese Space Agency Destiny Plus mission. And some of my colleagues at Arecibo have been doing shape model of this object to really be able to know where will the spacecraft go, and when will it be a good sampling site. So like I mentioned before, we can also refine the orbit. This is what we call astrometry. So we're able to know exactly how far it is and how it's moving, like where is it going. And as I mentioned, it's really good for shape modeling, right? For you to have a spacecraft to be able to fly to the asteroid and take images, it's really, really expensive. But for some cases, just with radar data, we can create a model of what the object looks like. So for example, the radar model of Tutatis in comparison to the images that were taken by the Chang'e spacecraft from the Chinese Space Agency. So it could be equivalent to spacecraft flyby. Like I mentioned at the beginning, it's good for finding satellites like Atira. There were two of them. One was really big, one was really small. Or for QE2, that you also see maybe the secondary moving a little bit faster. So it's really interesting to study this orbital dynamics. You really apply Kepler's laws and all of that part of orbits and basic physics that you think, oh, why am I learning this? They have really good applications in science, especially in experimental sciences. And like I said, sometimes we find some with three, like triples. This is asteroid Florence. It's about 4.5 kilometers. So imagine that distance, like 4.5 kilometers from you to what distance? Its moon is between 100 and 300 meters, and it rotates every 2.4 hours. So every 2.4 hours, it goes around itself. Like I said, radar is really good for space missions, just kind of reiterating that. For the shape, the surface properties, those are really fundamental information to know what type of instruments you want to send where would you like to sample? What samples could you obtain from that location? This is a table, a plot. I need to show some, I need to show some graphs here, right? We assign stuff. This is the amount of asteroids that Arecibo observed and detected up to 2019. The red ones are PHAs, these are the detected ones, and out of the total attempted. You see a decline right after Hurricane Maria. We're only able to observe until September. And why is this so popular nowadays? Well, surveys have been done by the Associated Press and the Center of Public Affairs from the National Optical Research Council. Most people and scientists are really interested in monitoring these asteroids and conduct scientific research on them. So it seems to people that it's more important nowadays to learn about these rocks in space than it will be to establish military presence in space. So kind of a little summary of what we've learned, what we talked about today. Asteroids and comets are leftover rocks from the formation of the solar system, from that protoplanetary disk that formed. When we study them, we can know about how the solar system formed, how it evolved, and we can know if there's any impact threat from them. Arecibo produces some of the best observations in asteroids and comets. It was the most powerful planetary radar in the whole world, transmitting up to 1 megawatt power. And it had the largest surface collection area as well. And knowing size, shape, and surface properties, rotation, astrometry, orbital dynamics are really fundamental information for being able to mitigate or divert any possible threat. And I'm gonna leave you here with a picture of a meteor that passed by Earth in 2019. It was detected by the GOES-16 satellite. It was 3 to 4 meters. And right there, you see the white part. It's acided, became a fireball and then landed on the ocean. So that will be the end for there. And if you have any questions or you guys want to talk about anything, let me know.
Well, thank you, Luisa, for talking with us about your pioneering work at the Arecibo Observatory. It's really phenomenal to hear about all that you have been doing. And I guess I never had delved into your work before. And so hearing about all the work that you're conducting at the Arecibo Observatory and still continue to conduct after Maria is just incredible. So now we are going to take questions from our audience, and a reminder that you may continue to submit questions into the Q&A box of your Zoom, and we are going to go ahead and answer as many as we can. So while we get some more questions from our audience, I did have one, and I wanted to know what happens with the samples that are collected on the asteroids, and how does that help inform maybe some of your future work?
Great, that's an awesome question. So of course, depends on the agency that took them, is what happens to the most of them. So for JAXA, the Japanese Space Agency, with the Hayabusa mission, they brought some samples. So they're gonna keep most of it, but they also share samples with the community. Like NASA did for the Apollo missions, we also shared some samples and tubes and pieces of it. So they can do spectrography, meaning you can see what it's made of, measuring different absorption and absorption lines. They can also see how strong it is, the cohesion, and pretty much everything you can think of with X-rays on them, chromatography, doing electron microscope technologies. Pretty much everything we can do to these samples, a scientist is going to try and do it. And then, of course, that information is publicly available once the scientists are able to compile of that scientific method process into a paper that then we publish, and the rest of the community sees it, and then somebody goes, I don't think you measured that right, or yes, I agree with that. And that's how we all share the information and get informed on that.
So I know that you spoke about how the radio telescope of Arecibo was affected by Maria. Can you tell us then what work that maybe you used to do before you're no longer able to conduct?
Can you repeat the last part?
Oh, yes. I was curious to know after Hurricane Maria impacted the Arecibo Observatory and also with its fall, I was wondering if there's any work that you used to be able to do that you're not currently doing, but hope to do in the future.
Right, right. So we lost the capability to do this, to produce the electromagnetic wave, hit the asteroid, and receive it. That whole part we don't have, but we do have. It's a lot of data from many years, over 40 years of data acquisition. So we're focusing now on that part. Maybe before we focused a lot on taking data. So now we are also have the opportunity to focus in, exploring that data and extracting more information.
Great. And we have one of our engineers is wondering, his name is Paul Olson, and he's from Virginia. He's asking, is the radio telescope open to tourism and can it be visited?
It actually just opened on March 10th. We opened our Science and Visitor Center, where we have really cool new exhibits. Some of that we were able to recover some key artifacts that have a historical and a historical aspect to them, right? That preserving them kind of has that historical perspective on what it was. So we have them on display. They're really big pieces, but we also have new exhibits inside the visitor center. So yes, you can come and visit it. It's really beautiful. The drive up to Arecibo is just another thing.
It's fantastic. And we actually have several classrooms in Virginia that are observing this. So their teachers logged in and they're observing this. So part of the mission of Reyes is to inspire the future scientists and engineers. And we would like to know if you can tell us what are some of the areas of study that your colleagues and yourself pursued, meaning it's not necessarily all astronomy, correct? You have people who are in physics and chemistry. Can you tell me about some of the backgrounds of people that work with you at the observatory?
So I personally did I've always been interested in space, right? In my high school, I focused in photography. It was a school specialized in arts. So I used to take a lot of pictures of the sky. And I did my undergraduate in physics, but I had the opportunity to do research in many areas of physics. So the applications of applied physics, the application of physics to environmental sciences, to chemistry, to astronomy, right? And the one I really wanted to do was astronomy. So in your undergraduate degree, you should definitely try and take as much math and physics as possible. So then you are able to apply those in whichever specific field you like engineering. That some of our colleagues are super important. They make our telescope runs and our systems function. We have computer scientists that help our computer networks and our data acquisition work, which is fundamental. We have people that are in charge of our management, right? They're also a direct part of the science taking part there. They need to know especially how that industry and how those things work. In the section, we have education. If you like that, it's very important that you know your scientific background. So it's not only a degree, an undergraduate to be an astronomer or planetary scientist. You don't need to have a degree in astronomy, but it will definitely, those classes will definitely help you shape and understand whichever field you want to focus on.
That's really great. And I really appreciated what you said earlier that anytime that the samples are taken, how they're shared with the scientific community. And again, just the knowledge that you create and others, our students who are watching could potentially build on in the future. So it's really exciting to see that piece too. And then I know that many of us have learned about asteroids from watching movies and how they're displayed on television. And I was wondering if you can tell us maybe about some of the close encounters that we have had where maybe you kind of were holding your breath about any near collisions with Earth.
Well, luckily we don't have detection yet of anything that is really definitely going to hit us or know when. Anyways, would you want to know? Maybe that will create more social panic, right? Maybe, I don't know. We haven't though had that, but I can tell you that the planetary defense community does hold annual or biannual workshops where we get people from from many countries and leading agencies to kind of explore that. What if there was such an object that could impact? How would the response be? What mitigation? And remember, this will be an international type of collaboration. So again, you could be part of all of this in law, in policy. There's all those areas that are also very important. So, but we have had, say, close graces, like 2019, okay, was an asteroid that I personally studied. We didn't discover it until it was just grazing by Earth, and it just flew really close, but it left really fast, which was good. We also had 2021 NK1. You can hear these weird names. Why is she saying years and letters? Is because that's how we name the asteroids, right? The name, when you read it, if it's a number and letters, is because it doesn't have a name yet. Like, for example, Apophis, that's an asteroid that we know by its name. But when it was discovered, it was called 1950 DA. That's by the year it was discovered, and the letters that follow are representative of what part of the month of the year it was discovered. So every year, when you look at those numbers, you see that every year we discover more and more and more. We have over 25,000 near-Earth asteroids that we know to date. So that is a lot more than we knew just 5 years, 6 years, 10 years ago.
And so I imagine too, with the advances of the instruments, as well as the science that you're developing, that you're able to detect more and more, right? As the instruments become more refined.
Exactly. As the technologies get more proven. Like James Webb Telescope is an example. It took a long time. I don't know if you know, this is the biggest telescope we've ever launched into space, and it has a lot of really cool sensors. You might recognize it in your mind because it looks like a beehive, right? It has these hexagonal mirrors. I invite you to just take a look at it and the capabilities it has, and the citizen science programs that they will also have later.
That's great. And can you tell us what are other applications of the technology that you've implemented to detect space rocks? So for example, could it also be used in detecting other near objects that are not necessarily rocks? Or I know that we hear a lot about all the space junk in Earth, and to avoid collisions with the International Space Station. Can you tell us about how the science that you're creating is also being applied to other areas?
To the technology itself used in Arecibo, because of the way the system was, we couldn't sap things that were really close to us, because it'll take, say, 3 seconds to reach the object in your Leo Earth orbit, like close to Earth. And then it'll take us 7 seconds to switch from transmit to receive. So we couldn't detect those really, really close objects. But however, we could detect things like what you said, like space junk. So we were able to, we had an object that we were to observe. And when we observed it, we saw that what we obtained from that data told us it was very, very reflective object. So since it wasn't comparable to anything that was, rocky or like that, we were like, it's got to be metal. So you compare with, orbital debris paths and all this. This is all online. You can find the satellites that are currently in space, the ones that were, and all that information. So we're able to identify that it was a module, part of a booster of a mission many years ago. We're also able to help in recovering the SOHO spacecraft. Like they lost it for a moment. And we've served as transmitter for the Lunar Reconnaissance Orbiter that is around the moon. The radar Arecibo actually started with the moon, observing the moon. We also observed Venus and created the first topographic map of Venus, because the radar signal could penetrate through Venus' atmosphere, letting us see the floor or the ground level. So it wasn't until Russia was able to have the first, say, mission in Venus that was kind of like an instrument that they let fall in the atmosphere, that they were able to measure, have information of the atmosphere layer. But with Arecibo, we're able to produce like topographic surface maps and also some information of this near surface.
Oh, that's great. And along those lines, what are some of the research opportunities for aspiring scientists who are interested in this kind of work?
So depends on your grade level. So if you are in high school, we do have a STARS program, but it's for students that are in Puerto Rico, where they do scientific research with the observatory scientists, like a pre-college Saturday program. So they take a research project and they see it through. For undergraduate students, we have our summer research experience from undergraduates that takes place in this summer. The application just closed last week, but it opens every summer. It happens every summer since the middle 70s or 80s. I might get that number wrong, but it's been around for a long time. And in that program, it's really cool. It's a great opportunity to see all the areas or sub-focus on one area of research. We also, different research groups have funding for having interns or for having students to help. And we do have about a few job openings. So you can visit the observatory website and go on jobs and see what current openings we have.
That's great. Thank you for sharing that. I'm sure that many of our students who are watching may be interested in applying, and if not for this year, for coming years, and we'll be following your work. And then what inspired you to go into your career?
I saw the comet Halley when I was really, really little in the 80s. And it looked like a little Q-tip that was distorted. And to me, that was just like, wow. I also was able to go a lot to like outside the city in Colombia, where I was born. I was born in Colombia. And I was able to go away from the city and see really the sky and being able to see that, like the Milky Way, which is something that we don't see now in the cities. You know, the light pollution is so great. It's so vast that many of you have never seen a true dark sky and all the stars that are there. So I think that was my main inspiration. Then seeing how the Challenger, the space shuttle program was going, and seeing all this, starting to see all the applications that space has, like our phones, like satellite TV, like being able to have this conversation. Like my phone, your phone has more computing power than what the Apollo mission had.
That's incredible.
Okay? Exactly. So seeing all of that really drew my attention, and then have the opportunity to work on near Earth objects. And I'm like, yes, I want to help not be the dinosaurs.
Can you tell us what other, perhaps like, who are some of your colleague researchers, and what is the kind of like latest and greatest work that you're embarking in this area of research?
So I guess what we're all focused in right now, it's in trying to help in the development of the next generation Arecibo radio telescope, that we can get funding, of course, and we can have a really good design, prototypes of having the next generation instrument. But with the legacy information, with all the data we have from the Legacy Arecibo Observatory, in the area of astronomy, we still have a lot of data for the fast radio burst. These are signals that we measured not long ago, and we're like, where is the signal coming from? Like, this is a signal we can't really, or originally we didn't really see. So as we're studying more data now that you know where the signal is, you can see if there were more. So that's really good research that has been done in astronomy, also measuring pulsars. We might not have the dish, but we have a lot of science data available. In my group, that is radar group, we're working on shape models. So like I showed, getting from those pixelated images to actually a shape model. One of our colleagues also works in deflection techniques. So if we actually were to have an object, what would be the best way to deflect it, right? It's not the same if you have a ball that's solid and you want to divert its orbital path than if you have a ball that's made of like porous material, like a spongy, like a porous stone, I think it's called, and you impact it, it'll brittle and it could create a catastrophe if you were to do that. So it really depends on what the object is made of, how its orbit is, to have a deflection technique. That's something that the DART mission is working on, to have a test of redirect. What would you need to redirect an object? It's going to asteroid Didymos, and it's got a companion that's called Didymoon. So the idea is to do a kinetic impactor on the small moon and see if that changes at all the orbital path of the system. We're also working on being able to compare information from the optical data to radar. What can we do with both sets? Are there objects we have both data sets for? And if so, what can we tell about the object with that? And then observing individual objects, that's one of the things that I'm doing, just focusing on individual objects and their characteristics. Which reminds me that I had here a question, if anybody knows the answer. Why are asteroids discovered with optical surveys or thermal imaging and not with radar? Don't Google it though.
We don't have any answers yet.
Okay, so we'll leave it there until we get an answer for a bit. Let's see.
We have one says because they are warmer than the background space.
Ooh, that's good. That's good. Why are they warmer? Come on.
The person said, come on.
So the moon, we see it because of the stars emit their own light, right? Everything else just reflects it. So you can see me and I can see you now because there's light being reflected. If you turn off the light, you don't see anything. So these rocks are traveling in dark space, but when the sun illuminates them, that's when we can say, oh, there might be something there. And like Paul said, because they're warming that background stars, yes, and they're also changing this direction, right? So when you look at this with a telescope in space, when you look up with your telescope, Earth is moving, so the celestial sky is moving. So you track the motion of the stars, and if there's anything that passes on your static image, well, that's probably a satellite or plane or an asteroid. So that's why we need light to detect these objects.
That's great. Or it could be another object that we cannot identify, right?
Right. But that we're learning on, like, Speaker asks about like Oumuamua,
yes.
That are objects that we couldn't recognize. That we're like, what is this? This is something completely different. That's something the data we have. So to answer your question, if they can carry evidence, well, why not? We don't have data on that, and we don't know yet the observations we have for the scientific community has for this subject. We're not very broad from many sites. It's pretty fast that everything happened.
And for those in the audience, the question was, is it possible that interstellar asteroids like Oumuamua carry evidence for extraterrestrial life? And I know when I visited the Arecibo Observatory, this is when I was a teenager in the 90s, I remember that they used to do quite a bit of listening right at the time to see if there's any life elsewhere. So I'm curious to know if that work still continues or if the focus is more on space rocks.
That work continued. We actually, the SETI Institute, Search for Extraterrestrial Intelligence Institute, had many servers and machines there that, I don't know if you are familiar, some time ago they had something called SETI at home. I think it's still available, where you could have your computer run in the background all this software to kind of identify any signals that could be different. So we can't do that anymore because we lost our ear with the antenna being lost. We still have, like I said, a lot of data that we can look into. What we do have now knowledge of is many, many solar systems. The number of solar systems in the 1990s went from like 2 to almost 3,000 now. So
incredible.
There are a lot of solar systems out there at different stages of development. Some that could be more like Earth, like TRAPPIST-1, or some that could be a little bit different, but close enough like Kepler.
So I know, I mean, it sounds like things are looking up for the Arecibo Observatory, which really warms our heart to know that, because it's such, I mean, it's such a key place for all of science in the world. And I'm wondering if you can maybe give us an update of when you expect that the Arecibo Observatory will be rebuilt again. Is it in a couple of years, or do you know how long the process will take, and what's happening? If you can just give us an update on what's happening there.
Well, I don't have an answer for that exactly. We're working on it, but we are open and working. We have, like I mentioned, other instruments still available that's focused on studying the atmosphere. So, and also these meteorites or objects that could, come in contact. We have a LiDAR facility, an optical facility, and our Science and Visitor Center, it's open. We do have partnerships with other telescopes. And we are having more active our 12-meter antenna. So we're really working on having that instrument as a starting ground again for astronomy.
Well, thank you for that update. I know that we are all going to be following and hopeful that soon the Arecibo Observatory will not just be how it used to be, but many, many times better. So those are all the questions that we have today. On behalf of Old Dominion University and the REYES program planning team, I would like to thank Luisa Fernanda Zambrano Marin one more time for joining us today. We will continue to follow your professional journey and its impact on aerospace for many years to come. And I'd also like to extend my gratitude to the Office of University Communications, the Puerto Rico Space Grant Consortium, who connected us with you, and the Office of Distance Learning for their support of this event. And to our audience, thank you for tuning in. For more information about our free virtual summer program, visit odu.edu/reyes, that's REYES. We will be opening registration for our summer virtual program soon. So our team is putting together all of the programming as we speak, and we look forward to you joining us on June 27th. So today's session has been recorded, and if you'd like to watch it again or share it with friends, you can access it from the REYES website at odu.edu/reyes. This concludes